In this video, we're going to learn how to determine the hybridization of different orbitals. Let's jump right in with an example. Here I have CH3, Cn. So your very first step is to draw out the Lewis structure. So we know we have our CH3, which is our methyl group, bonded to 3 hydrogens, bonded to carbon, and then triple bonded to nitrogen with a lone pair on it. Our second step is to determine the number of sigma bonds plus lone pairs attached to each atom. So let's just go ahead and look at nitrogen. We see that there is 1 sigma bond and 1 lone pair attached. So 1 plus 1 is equal to 2. And from this we can find the hybridized orbital. So 2 is equal to, so the number of orbitals in is equal to the number of hybridized orbitals out. So 2 is equal to S plus P, which gives us sp. So nitrogen is sp hybridized. Let's move on to the carbon beside it. So there's 1 sigma bond here, another sigma bond here. So again, 2. S plus P is equal to sp. Again, sp hybridized. Looking at the last carbon, we have 4 sigma bonds to it. So 1, 2, 3, 4. From there, 4 is equal to, and we'll go more in depth here, S plus px plus py plus pz, because this is 3-dimensional. So from here we get sp3. So we just go ahead and label that sp3. To determine bond angle, it's important to remember that these orbitals want to be as far away from each other as possible. So just looking at this, we have a linear structure. It's on a 360 plane, so then between them is 180 degrees. We can say the same for this middle carbon. Now the last one is a bit trickier. So this just isn't just on a 2D plane. We have our x, y, and z. So that means the angles between them aren't 120 degrees, but 109.5. Here's a second example. Go ahead and draw out the Lewis structure for both of its resonance forms, and go ahead and label out the hybridization for each atom on both forms. This should be the Lewis structure that you end up with. Remember, you obtain your other resonance form by pushing these 2 electrons into a pi bond, and then pushing these 2 electrons out of a pi bond to become a lone pair. Assuming you've already done this and labeled the hybridization, I'm going to speed run through. So carbon, 4 sigma bonds, sp3. Carbon, 3 sigma bonds, sp2. Oxygen, sp2. Nitrogen, sp3, because of our lone pair here. So our methyl group hasn't changed, still sp3. Same with our central carbon, still sp2. However, we'll notice that the oxygen here is no longer sp2. It's sp3 because it now has 3 lone pairs and 1 sigma bond, so sp3. And our nitrogen is no longer sp3, it's now sp2, also with a positive charge. So now sp2. Now the question is, what is our nitrogen then? What is our oxygen? Well, we find this out by comparing the two and picking the lowest hybridized orbital. So here we're choosing, okay, oxygen, sp2 versus sp3. Well, we'll pick sp2, it's the lowest one. Same with nitrogen, sp3 versus sp2. Well, we'll choose sp2 because it's the lowest. So if we were given this problem, then we will label our nitrogen as sp2 and our oxygen also as sp2. And this works really well, because remember, they're resonance. They have electrons that need to delocalize. And with sp2, you know that you've already hybridized your s, your px, and your py. But you still have a remaining pz that is unhybridized. It hasn't been merged with the others. So then it's this pz here that's across these empty p orbitals that allows these electrons to delocalize over our molecule, which is ideal for resonance. Here are the practice problems for this video. Pause it and good luck.